Okay, here's a question about standing waves. The diagram shows a standing wave of wavelength lambda, which has been set up on a string of length L. Okay, the string is fixed at both ends. Immediately we know both ends are nodes. For the standing wave, state the relationship between lambda and L. Here, there is no formula that we memorize, we simply count. Here's one lambda. Here's another lambda. Here's another lambda. And one more lambda. There's no half wavelength. We have L equal to 4 lambda. Label two antinodes where the string is vibrating in phase. That means don't label this antinode and this antinode. They are completely out of phase or perfectly antiphase. Instead, we could label these two, A and A. We are told to use the letter A. Or if you wanted, you could have labeled these A and A, but you don't want to label two that have a different phase. Okay? Check. The standing wave has a wavelength lambda and a frequency f. State and explain. With respect to a standing wave, you always want to focus when it says with respect to. They're telling you what one of the points is. One of the three. State and explain what is represented by the product f lambda. Well, we know that c is equal to f lambda. But a standing wave is not moving, it's not traveling. So what is speed when we're talking about a standing wave? That's what they want us to do right here. They want us to refer to the fact that a standing wave is produced when you have two identical waves moving in opposite directions. So let's do that. A standing wave is formed by two traveling waves moving in opposite directions and continually interfering. The product of f and lambda is the speed of these traveling waves. On to the next one. A string is attached between two rigid supports. That means that these supports can't move, so we have nodes. It's made to vibrate at the first harmonic frequency. Here is the string at t equals 0. Here are all the displacements for every particle along the string, like that. Draw the displacement at t equals 1 over 4f and 1 over 2f. What are they saying? Well, 1 over f, we know, is the period. So this is really like saying the period over 4. And this is like saying the period over 2. So after half of a cycle, after t, big T over 2, it is at a mirror image. And at a quarter of a cycle, right here, at a quarter, it's halfway between this and this. So it's flat across. The distance between the supports is 1 meter. A wave in the string travels at 240 meters per second. Find the frequency f1. Well, we look at the picture and we say, hey, a full wavelength would be like this. So L here and another L would make 1 lambda. 2L is equal to this first wavelength. You can do it that way and reason through, or you can memorize the equation. N lambda n equals 2L. We're talking about the n is 1, the first standing wave, the first harmonic, and we get the same formula. So if we plug in L, we get 2 meters for lambda 1. Next, we turn to the wave speed equation. We're going to plug in lambda 1, and we're going to calculate F1. Speed is 240 meters per second. Lambda is 2 meters. The meters will cancel. We'll be left with inverse seconds, which is a hertz. And F1 is going to be 120 hertz. An organ pipe that's open at one end only has the same F1. The speed of sound in air, so the organ pipe is like this. Air is what vibrates. F1 looks like this. And the speed of sound in the pipe, the speed of the waves in the pipe, is 330. Determine the length of the pipe, L. Okay then. For the pipe, we know that we have a different equation. N lambda n equals 4L for a pipe that's only open at one end. We're dealing again with the first harmonic. So we have this equation. We're looking for L, so we first, if this is our unknown, we first must find lambda 1. Okay. F1 for the pipe is 120, because it's the same as this answer. We know C is 330. So we're looking for lambda 1 in order to plug that value in and calculate L. Lambda 1. That's our unknown for now. We use the wave speed equation. C is 330. We're plugging in F1 and seeking lambda 1. So 120. We divide. It's 2.75 meters. That's lambda 1. And then we say L is lambda 1 over 4. I'm getting that from down here. So 2.75 over 4 gives me, we round for sig figs, only 2 sig figs, because you see 330 has 2, so 0.69. 0.69 meters. On to the final question. It's about standing waves on strings. A string is fixed at one end, and the other end is free to move up and down. Explain how a standing wave can be formed. Now, we know there's a generic explanation for how standing waves are formed. We talk about how the incident wave and the reflected, or in this case, it might look like this. The incident wave and the reflected wave travel in opposite directions. They interfere, and at certain frequencies, they meet the boundary or they satisfy the boundary conditions. But in this particular case, what are they looking for in these 3 points? Well, to be on the safe side, I strongly recommend focusing on the information that's given. So they gave us the boundary conditions, right? This has to be a node, or well, they gave us enough information to figure out the boundary conditions. And this must be an antinode. So I would recommend referencing those facts. Use the information to answer the question. So the first thing I'll say is the fixed end is a node, or must be a node, and the free end must be an antinode. At certain frequencies, these boundary conditions will be met. at those frequencies, the incident wave, or waves, and reflected waves will interfere to produce a standing wave. Now that's probably an overly thorough answer, and if you check the answer key, it's going to be way more thorough than they're required, but you never quite know exactly what they're looking for in the 3 points, so being thorough guarantees you will get all three. Maybe they choose, one part of the explanation over the other to give the point, to earn the point. So you want to have all of the parts of the explanation to make sure you get all of the points. The diagram shows a string vibrating in the fundamental or first harmonic. And again, we're not really going to see the word fundamental in the IB physics class. They will use the term first harmonic, not fundamental. And then you probably won't see the word mode, but it's just the frequency, the first frequency, F1. Both ends are fixed. Okay, so this is not the wave that they talked about up here. Different wave. Label an antinode on the diagram. An antinode is right here, because that's where the particles go really far down and really far up. A. Or AN. The length of the string is 0.85 meters, and the fundamental frequency, again, they won't say fundamental, they'll say F1, the first harmonic, is 73 hertz. Calculate the speed. Well, speed is F lambda. We're dealing with the first frequency and thus the first wavelength, but we don't know lambda just yet. So we use the equation for a string tied down at both ends. We're talking about n equal to 1, the first harmonic. So 1 times lambda 1 equals 2L. And lambda 1 comes to 2 times 0.85. That's going to be 1.70 meters. Or I guess 1.7 with sig figs. So then we plug into the equation. The frequency is 73. Lambda 1 is 1.7. Frequency is in hertz, that's 1 over seconds. Lambda is in meters, so we have meters per second. 73 times 1.7. 124.1 meters seconds to the negative 1, and if we round for sig figs, it's actually going to be 120. 2 sig figs in this value and in this value. Sketch how the string appears if it's vibrated at 3 times the frequency. Okay, so we're going up to n equals 3. The third integer multiple, n equals 3. So n equals 3, you have 3 times, well, let me try that again. Just move the end over. Something like that. Whereas the first wave had only 1 antinode, here we have 3 times as many antinodes. The wave is 3 times as frequent. State the speed of the wave when vibrated at this new frequency. It's the exact same. Speed does not depend on frequency, so we have the same speed. Speed is fixed in a given medium. As long as you don't change the properties of the medium, like the temperature or the tension of the string, this will be true.